Okay, this is the second in a series of videos about reaction dynamics for CHE30042. Here we're going to start talking about collision theory, and actually we're going to derive collision theory from first principles. Other resources for this part of the lecture series can be found in these two textbooks here, Reaction to Kinetics or Elements of Physical Chemistry. And again, I've got QR codes that should lead you to websites where you can access these things online. As before, this QR code here for Elements of Physical Chemistry will lead you to the Biblio website and takes you directly to the page number, whereas this is for the Script website, and it doesn't take you to the pages, but you can find it quite easily from there. I don't actually have availability to physical chemistry online, but if you do have a copy, then you can go to these pages to read up about this topic. Okay, so where does collision theory come from? Well, collision theory basically is the simplest reaction dynamics theory, okay? And it's trying to come up with a construct, a way of predicting how reactions might go based on just some very, very simple, relatively measurable molecular parameters or parameters for the species that are reacting, okay? Makes several key assumptions, the first of which is that the reaction species are actually hard spheres. So hard sphere is something where you don't have any repulsive or attractive interactions until you get to the absolute edge of the sphere itself, okay? At which point in time there's a repulsion which is infinite, okay? So away from the sphere you don't have any interactions at all, and then once you get to the edge of the sphere, you cannot go any further, essentially. So we would describe hard spheres as being acting somewhat like billiard balls. So of course, if you have two hard spheres banging together or colliding, then in that case, the shape and the size are maintained because that's basically what happens when you have two things and where there's an infinite potential energy when they try to get closer than their outer radii. Okay, so that's the first key point. The second key point of collision theory is that molecules must collide. Now that's not particularly surprising given the title of the theory, but that is required in order for any reaction to proceed. I would say there's a bit of a caveat to that, as you'll see in the next video, whereby reactants might not necessarily have to collide, but can get driven to collide. But nevertheless, there has to be a collision eventually. Third thing is that once a collision takes place, if the molecules don't have enough energy to react, then the collision will not be successful. And so collision theory needs to be able to measure whether a molecule has enough energy to react or not. Okay, and so that's part of the theory. So if you've got, essentially we're going to go back to our biomolecular elementary reaction that I introduced in the previous video. We've got A colliding with B, and that collision generates product P. Again, just as we had before, we have a rate equation for this process. It's a second order process, so it's the rate is proportional to both the concentration of A and the concentration of B, and the rate constant is K2. Okay, so this is just a general rate equation that you should be familiar with making. Collision theory therefore predicts this. So it predicts that the rate is proportional to the molar collision frequency, which is this Z here, multiplied by the fraction of successful collisions. So, if your fraction of successful collisions is 0.8 and the number of times it collides is, 1 per second, then you're going to get 0.8 successful collisions per second. Okay, and that's all that is essentially saying. So what we're going to do is we're going to actually try and make this a little bit more user friendly and try to actually put some parameters in here that we can actually, because we can't really initially just calculate anything based on just these two parameters. We don't know them, but maybe we can actually figure what they might be. So the overall rate equation, just to remind you, is this. And what I'm going to say is, using collision theory, we can derive this relatively horrible looking equation. Okay, now this looks pretty horrible, but I would note to you that there's quite a lot of constants in here, and that's the case for many of these equations that we talk about in these lectures. And what we're going to do during this next sort of 20 minutes or so is we're going to derive this equation from the beginning and explain where all these places from. But as a bit of a preview here, Okay, so you've got a part in here in the green brackets. This is accounting for the speed that your molecules have, and it's the mean speed across both populations, A and B in this case. Okay, this bit in the red brackets here, this is accounting for the fraction of successful collisions. So this is actually quite similar, well it is the same as the Arrhenius exponential. Okay, you've got constants such as the Avogadro's number, and I apologize, but throughout this course the Avogadro's number is capital L. Okay, so you're going to have to get used to that and be able to recognize that as capital L, not capital N with a subscript A, as you're probably used to. Sorry. And then you have two other parameters here. This one here is basically telling us about the size of the molecule. So it's basically saying that the bigger the molecule, the more likely it is to collide. And finally, you've got this term here, which is basically just a constant. So E here is Euler's number. So that's, ln is log to the base E. The natural log is log to the base E. Euler's number is about 2.7. And this is just basically allows for agreement with Arrhenius. And by the end of this this video, you should be able to know what that means. Okay, so that's what all of these bits in here. So they all actually have really good meanings. We can actually put it all together based on sort of working out where these bits come from, and that's what we're going to do now. Okay, so first thing we're going to do is we're going to talk about the influence of molecular size. Okay, so we've first got, in order to do that, we've got to think about what we're going to do. Okay, so essentially, if I am a molecule and I want to know how many times I'm going to collide with another molecule, I can see myself as moving through a tube. My tube alone just has a radius of my radius. Okay, so the radius of A gives a tube that is defined by these dotted lines here. Okay, however, we can then define a sort of a collision radius. Okay, and that would give us the sort of the tube within which I'm going to collide with the molecule B, and that will basically be the radius of B plus the radius of A. So, for example, if I've got my molecule coming through here, coming like this, if B is sited here, then A is going to miss B because B is the radius, B isn't actually within its flight path, okay? Whereas here, it's just going to hit it. And of course, if this sphere moves slightly down, it might just graze it. And the point at which it stops hitting it, or, the point above which it stops hitting it, is the radius of B plus the radius of A, okay? So this is a miss, this is a hit, and this is a hit. Okay, so this tube here, this red tube, is defining that collision volume, as it were. Now, there's a couple of things we have to do here, one of which is rather than saying we have a volume, we can actually say we have a volume that's dictated by an amount of time. So we've basically got our molecule moving, it's moving at a certain speed. If it moves at a certain speed for a certain amount of time, then it has covered a certain amount of distance. And so therefore, that's where we get the distance from. But it's also where we get the molecular speed from that I talked about in the previous slide. But anyway, this is how we define the sort of collision volume that we've got. Okay, so key collision geometry terms. First and foremost, we have a collision diameter. Okay, which I mistakenly referred to as a radius a minute ago, but it's a diameter because basically it's two radii added together. It's a bit confusing because the diameter of the collision volume, this cylinder here, the collision diameter is actually the radius of this collision volume. Don't blame me for that. That's something that someone else came up with a long time ago. Okay, and you're just going to have to get used to it. But basically, the collision diameter is given by the radius of B plus the radius of A. Okay, the collision cross section, therefore, just by simple geometry, is given by pi times by the diameter squared. Okay. The collision diameter squared, or pi times the radius of this cylinder squared. Yeah, and finally the collision volume is given by the cross section. This is just an equation for a volume of a cylinder. Okay, so it's the cross section multiplied by the distance here, and the distance here is given by the speed that the molecules are traveling at, or molecule of A is traveling at, multiplied by the time it's traveled for. Yeah. Okay, so these are just some key terms, and this cross section is the really key one because that one goes into the collision equation. Okay, from this we can therefore say that if we have just stationary molecules of B okay, and we have a molecule of A passing through these stationary molecules of B, we're going to have this number of collisions per time t. Okay, so this is going to be our number of collisions. Yeah, it's going to be given by the number of molecules of B over the total volume multiplied by the collision volume. Okay. So that's great, and we've got this equation here, which is just the one that we've got from the previous slide, this equation here. Okay, this is fine, but of course there's some problems here, one of which is that, well, if my A molecules are moving, my B molecules will definitely be moving, just because that's going to definitely be happening. And therefore what we have to do is we have to take that into account. And we actually, instead of using just the speed of A, we need to use the mean relative speed of both molecules, A and B. The second thing we have to do, or the second thing we can do to make things a bit easier, is if I set this to 1 second, this time, this t to 1 second, then effectively this t becomes a 1, and then we're just basically saying that z is per second. Yeah. Oh, yeah. The next thing we can do is we can just take into account the fact that we've not got one molecule of A either. We're going to have a lot of molecules of A, of course, unless you have a homeopathic dilution, which we don't normally have in chemistry. We're going to have many, many molecules of A, and we can say that the number of molecules of A is dictated by Na, and this is the reason, by the way, why we can't use Na as our Avogadro's constant. So we have Na molecules of A per total volume V. Okay. So Na over V is going to give us our number density of molecules of A. Okay, and then from that, what we can do is we can basically write a new expression for the collision frequency, which is now this term here. Collision frequency ZAB is given by the number density of A multiplied by the number density of V multiplied by the speed, the relative speed, and the collision cross section area. Okay. And I'm going to tell you now that this is the same as writing this equation out here. And I've just explained why that is down there. And I'm not going to read this out to you. I'm going to let you figure this one out. But basically, it's that the number density is related to, you can convert the number density into a concentration quite readily by doing this here. Don't forget, again, that L is Avogadro's constant. And so we finally have our expression for our molar collision theory frequency, which is basically the collision frequency divided by Avogadro's constant, and that is given by this equation here. Okay, and we're going to take that forward to the next slide. Okay, so we've got a nice equation for the molar collision frequency, but what we haven't got yet is an idea of how to calculate that speed. Part of the equation. Okay, and in order to do that, we need to go back and think about the Maxwell distribution of speeds, which comes from the kinetic theory of gases, which is referred to right at the beginning of the Elements of Physical Chemistry textbook. And we can also just refer basically to the Boltzmann distribution of energies that you covered last year. Basically, we end up with a distribution of speeds that looks a bit like this, and we get an equation here for the mean speed of a given of molecules within a distribution of molecules. Okay, so it's related to the mass of the molecules and the temperature, basically. Okay. Of course, in our case, we don't just have a single type of molecule. We have two different populations of molecules, A and B, and in that case we actually need to change this equation very slightly, and instead of having the mass of a single species of molecules, we have to take into account the reduced mass of the two species A and B here. So that's given in the usual way, but that's really the only difference between these two equations. So that basically gives us a final expression for the molar collision frequency, whereby we basically substitute in this here for that relative velocity we had before. And already you can see this is starting to look an awful lot like that collision theory equation I gave you right at the beginning of this video. So just remember that collision theory doesn't just include the molar collision frequency, it also includes this fraction of collisions that are successful. And so now we're going to move to talk about this fraction of successful collisions. Okay, so yeah, we now really need to find this F. And again, we can go back and look at the Boltzmann distribution and recall that, you know, if we've got a low temperature, then we're going to have our molecules are generally going to have less energy. In this case, it's referred to by speed, but you know, energy is going to be proportional to speed. In this case, kinetic energy. So you know, at a lower temperature, we've got less energy, and so therefore, you know, if we want our molecules to have a critical energy or a critical speed, then we can increase the temperature in order to make sure that a greater population of these molecules have that energy or speed. Okay, so that's what the Boltzmann distribution basically says, and it gives us the maths with which we can calculate the fraction of molecules that do actually have such energies. Okay, and you know, doing that, we can end up with this equation here for the fraction of collisions with an energy that's greater than our activation energy here. And if you want to know where this equation came from in a bit more depth, I do have an additional handout in which you can see the derivation for that highlighted. Okay. So the key point here is, of course, that if the activation energy is high, so if we move our activation energy in this direction, or our activation speed in this case in this direction, then you know, fewer molecules would have energy versus moving it back this way, where, you know, if I put it here, for example, you'd have like about 50% of the molecules would have the energy required. Okay. So we're now in a position where we can assemble our collision theory equation. So we started with this here, which is just basically saying that the rate is related to the number of collisions times by the fraction that are successful. We've got an equation for the molar collision frequency, which we worked out. We've got an equation for our fraction of successful collisions, and so that therefore all we have to do now is basically substitute this in for this, and this in for this in this equation here, and we end up with our collision theory equation here. Okay. Obviously, this is for the rate, but we can also find an expression for the rate constant itself. And this will be particularly useful because we can then compare this to, say, for example, Arrhenius theory, which doesn't relate rate to temperature and to activation energy, but it relates the rate constant to it, doesn't it? And so we just remember here that the second order rate equation is given like this. So essentially, you know, all we do is we leave these two things from this equation here, and we get our expression for our rate constant. So our rate constant expression is written out like this. Now, I put an asterisk next to this because this is the rate constant before experiment is taken into account, and I'll show you what I mean in the next slide. What you'll note is basically here what we don't have is that Euler's number to the power of a half, and really that Euler's number to the power of a half is the thing that just makes a slight tweak to this collision theory in order to make it agree with Arrhenius theory. Okay. But slightly annoyingly, in order to take experimental activation energy into account and to work out if we can directly compare collision theory pre-exponential factor with Arrhenius theory pre-exponential factor, we do first need to do some relatively horrible maths. And the key point on this slide is that the K2s are the same, and what we're trying to work out is whether this activation energy here is the same as the experimental activation energy here. Okay. So in order to do this, we have to do a bit of maths. So the first thing we're going to do is take the log of both sides of this equation, and likewise the log of both sides of the Arrhenius equation, and these are the results here. And again, you know, I'd like you to work through this yourself. This is just using the law of logs to get this result. Once you've done that, you need to then differentiate this equation with respect to temperature. And again, you obtain this, and this term here, I mean, all of these terms are constant with regards to temperature, so they all disappear. This term here comes from that one there, and this term here comes from that one there. And likewise, we're going to take the logs here, and we're going to differentiate that with regards to temperature again, and again, we get the same thing here. And this is the same result here from here as this from here, okay? So, you know, if you do need to revise those things, then please do. It's not essential for understanding this course, but nevertheless, it's useful to know where all this comes from. Okay, so as I said already, the K2, so the rate constants are the same, and so therefore we can say that this is equal to this, because, you know, these two are the same. Yeah. So that's what we've done here. And then we can basically rearrange this and simplify a little bit. And from that, we end up with this term here, which is basically saying quite clearly that the experimental activation energy is not the same as the activation energy that we've calculated so far in collision theory, but it's sort of similar, and it differs by this RT/2 bit. Now, in order to work out, how we can put this back into the equation and how it affects the collision theory equation, we can basically, instead of having minus EA in here, we can essentially substitute that for this, which comes from a rearrangement of this part here that's in the box. And if we just essentially then simplify, we end up with the exponential term that you get in the Arrhenius theory multiplied by the exponential of a half, or e to the half. Okay, so that's just that really, and so that's where that e to the half term comes from in that collision theory equation that I said at the start, and this then is the final expression for the rate constant predicted by collision theory, and this is the one that you should use if you're doing any calculations on collision theory.